Okay, good to see everybody on. This is episode 69, February 9th, 2023. So I'm going to go over this slide here. And so basically, it's neuroradiology. So this is more about classification than it is about making better images. And there's been a number of approaches with this. And I chose some of these papers. So there's a decent amount in Alzheimer's disease research and quantum so far. So as you can see, 2022, 2023, um, you know, and two different types of databases, Kaggle and ADNI, with some good results. I'm going to go over some other significant findings in this as well. And so this is Roche and QCware. Strangeworks, Deloitte, IBM and Amgen, and then some of the updates with the startup as well. So here we go. So this is the table that I created. So basically in all of this, the key is to get the highest accuracy or the classification accuracy. So you see in the first row here, the Shahwar et al. February 2022, ResNet 34, which is a convolutional neural network. And then you have, we'll just go across the row. So you have, Kim Ryan using a ResNet 18, and then the newer of the Shahwar papers using an AlexNet 8 layer. So these are all running on conventional classical computers or GPUs. Now, the data sets that they used are a little bit different. So as you can see here, you have Kaggle, and then for two of them, and then ADNI. So ADNI is the more standard one that you'll find in the bigger papers, and they're kind of stepping up from this Google Kaggle to Alzheimer's disease neuroimaging database right there. So you can see, so learning rate is set at 10 to negative 4, training testing between 90 and 10 or 80-20. And you're going to see this as far as hyperparameters. You have atom optimizer, cross entropy function, and those are all the same across. Now, the things that makes these three papers unique is the quantum variational circuit. So it's doing specific things on classical, these larger neural nets, and then other things that bode well, using a quantum simulator, this penny lane quantum simulator at 4 qubits, to get some advantage. So in these days, you have to search hard and you have to plan your experiments right in order for that to come through. So you see, so epochs is basically sending through data and sending it back. So most of these were either 20 or 25. Batch size increases, over the years, going from like 8 to 32 to, for the most recent ones. And the ML framework is typically PyTorch. Now, what happens is you have a big image, and then so you'll have a feature vector of 512 that'll get reduced to 4, and then when it gets reduced again to 2, this is this hybrid classical quantum approach. That's a binary classification. So as you can see in the results here, is that at the bottom, 97% for the first one, and then the second one is 98%, the third one is 96%. But the third one is, without a doubt, the better paper to go off of. It's got the better databases, larger feature vector, a higher batch size than the original one. And the rationalizations seem to make the most sense in that one. So here's the first paper. So this is the first column. So this is Shahwar et al. And it's basically automated detection of Alzheimer's via hyperclassical quantum neural networks. And basically it's a feed-forward neural network with a ResNet 34. And I'll show you some of the architectures with all these. But, we're talking, to use quantum mechanics in a quantum simulator, some of these other figures that they show is it's kind of like topping out at like 4 or 6 qubits, just for a variety of reasons as far as your best accuracy, closest to 100%. Now, you'll see this a lot. So, fixed depth. So quantum circuit consists of quantum gates with a fixed depth and is the central part of the quantum layer. Quantum QVCs or quantum variational circuits consist of a state preparation layer, variational layers, and a measurement layer. And I'll show you a figure with that. And then also you have quantum transfer learning, which is resilient, expressive, and computationally power. It's basically saying, saving on energy costs in the long run. Now, I've shared this before, but now it just makes more sense. So you have these databases, and again, this is the first paper. It's Kaggle, so it's Google. So you get these, I downloaded the data set, and it's like 4 different types, but basically they're just doing binary, just looking at 2 of them. And it goes through the ResNet 34 as usual, and then you take that 512 feature vector to a quantum variational circuit, and then that's run in a quantum simulator these days. Now, keep in mind, most of those, will max out at like say 30 or 40 qubits, just because they would require so much RAM. And then it goes through to this fully connected layer. And the interesting thing that I saw is basically a fully connected layer. It looks like can be obtained using ion trap technology. So what this means, this is a very small portion of what we can do in quantum as an industry. So, maybe a future ResNet or an AlexNet, that runs off ion traps because their qubits are not just nearest neighbor. And then after that, you have your classification. So this goes to, your binary. So it's demented or non-demented there. So this is ResNet 34. And the key with all this is it's still kind of truncated because, typically you do convolution and pooling. But, you see these 4 big layers, batch process, you're defining these specific variables before you go to run. And, say at a given, output, then it's sending this classical data to a quantum. So this is a zoom in to the previous slide, which kind of showed the whole hybrid classical approach. So here's a zoom in on the quantum section. So you have encoding coming from ResNet 34 classical data to the 4 quantum bits. Now, there's a little bit more behind this than I put, but basically, you have the initialization layer. You're achieving superpositioning at this stage at the Hadamard gate. At the rotational gates are embedding, and this is you're converting from classical to quantum data to do a specific task, and then at the end of it, you switch back to classical. Now, you can see the layers are repetition. So these plus blues are called CNOTs, and then you have rotational gates, so that repeats, so for a total of 6 times. And at the end, it's kind of interesting because you can't run a quantum computer without classical, and here's why. So if it shows up on your screen there, so you see the 4 quantum bits, Q0 to Q3. Now the C4 is the classical bit, and that's represented by, it's a double line that goes the whole way across the trainable variational quantum layers. And then, at certain points you measure, and then this collapses the quantum effect. And then it's part of the decoding process that gets sent to this fully connected layer. So here's the thing, fully connected, maybe potential as a, ion trap technology for bigger neural nets than this kind of a smaller one. So transfer learning, you'll see a lot, and fine tuning, feature extraction, and this hybrid method. It's suitable for high-res images, and if you look at some of the other articles that I'll show you, is a lot of times they have to be reduced down to say 25 by 25. But still, it's your end result that matters. After going through hybrid approaches, or if you just have a orthogonal quantum neural network that you're working on, and what's the classification accuracy and all these kind of things. Now, the ResNet is peculiar because it uses skip connections. So, sometimes it gets run through in epochs, number of times, but on certain times it skips. So it's one of the more effective, and this is not new to classical computing. ResNets have been around for some time. So I kind of touched on this a little bit, the hyperparameters. So, epochs, and, all these things are adjustable. Now, these 3 papers, I would say, are kind of similar, right? And just changing a data set or adding, different number of batch, size to it. But you'll see this a lot too. So you'll see cross entropy loss function is used for the actual classification part. So it's like a journey that you're on through this data, classical to quantum, back to classical, then classify. Now, here's the results versus others. And then, so keep in mind, trying to see data sets, they just say MRIs. But in this first one, the 97%, again, they improved upon it later, and they're using Google Kaggle, which isn't, you don't see that as much in kind of like the big papers such as ADNI, databases. So for comparison, but regardless, 97% for their hybrid, CNN and QVC, and it is possible to, strike gold with some quantum approaches. So this is a 4-qubit quantum computer. It's dressed. So dressed means it's in between two other classical layers. And there's 2 other papers that kind of support this. So here's the second paper here. So this is Ryan Kim, basically. And a lot of it just overlapped with the other 2. And this is the basic one. So you see the convolutional, pooling layers, and it goes through QVC, very similar to before, penny lane cascade. It may have been a little bit different on a simulator because this is air device versus, default device for the other 2. Classical fully connected layer, and then your classification at the end there. And here's just the overall kind of approach to this. Again, some things, and I believe that this one was 6 layers, but they used the ... and I couldn't find it in the rest of the paper. But figure it's very similar to the other 2. Now, this is the update. So this is what I'm basing a lot of, it's a good platform to kind of go off of. Alzheimer's data sets, ADNI data set. So they, instead of 512 features, they bumped it up to 4096. And then it's the same kind of setup as before, this 4-dimensional vector, 1 qubit equals 1 dimension. And then the vector transformation into 2 dimensions for classical, classification, binary classification. And this time they didn't use ResNet. So the first one used a ResNet 34. The second one was a ResNet 18. And that's just the number of layers. So there's more comparable within ResNets compared to like an AlexNet, which only used 8 layers. So there's just little differences on the conventional part. So basically, you have the ADNI data set. It goes to AlexNet, Quantum Variational Circuit, run on a quantum simulator, and then back to the fully connected layer. And then you'll see the output is either demented. So this is, you have Alzheimer's or you don't, based on this binary classification. Now this is it. So this is the AlexNet. So the first 2 layers are repetitive. So convolution, rectified linear unit, and then pooling. And then you see the same thing for the second layer. Now the third layer doesn't have that. It just doesn't have the pooling. It just has ReLU. Same thing with 4th, 5th. 5th looks more like 1st and 2nd, and then 6th. So these things are just, they've been optimized over the years. And, the quantum potential in the future all depends on the hardware, because if you're limited in, quantum simulators to 4 to 6 qubits, where that's kind of your sweet spot, you're getting good results, then, as the better ion trap or gate-based superconducting qubit comes in, then you can start to, and especially for ion trap, because it's all-to-all connectivity, you can start to make that argument of having, quantum convolutional neural networks in sizes like this as things get under control with the, more qubits and less error. And then this is what they call the trainable dressed quantum circuit. So this is the zoom in, as I put it in the bottom. So you're going AlexNet classical to quantum, and then back to classification paths here. And some of these explanations are pretty good that they offer in the papers. In the future, basically, to do multi-class classification. So multi-class is tertiary or quaternary. So tertiary would be like non-demented, mild cognitive impairment to Alzheimer's disease. And you can go quaternary, such as, stable MCI to progressive MCI and so forth. And to build, the ones that were gone over in these three papers, you could build a variety of different variational circuits, for performing these tasks. Now, the upside with the quantum simulators is there's absolutely no noise. So you're limited by basically a classical computer and memory, those types of things. But I'll get to another paper because it talks about how many they did over 1 billion shots. And if you were to do that strictly on a quantum computer at a penny a shot, that would be $10 million. So a lot of these are run initially on quantum simulators, get the bugs out, better understand what they're doing. And then basically what they're saying is, there's hope. There's definitely hope in imaging, for quantum, reduce computational power to help improve the speed of the network as well. And this means neural network. So here's the ADNI these are the ADNI competitors. So you see the closest one is this DEMNet that pops up 95.2%. So 64 reference through 69 are all on conventional, CPUs, GPUs, that kind of stuff. And this proposed method uses the AlexNet, convolutional neural net with the quantum variational classifier that's run on a quantum simulator. And you can see just a little bit better than the DEMNet. So it's very promising. So in a lot of the papers, they'll put the algorithms. So this is the first paper, the most left column on that table. And, basically, there's not a whole lot of complexity, but what matters is what it's doing through each of the layers, and it keeps being, sent back through epochs. And then you see the bottom algorithm that they provide in the data set as well. Now, a lot of this just reminds me of scientific method, because if you have the first paper and then they're iterating more on it, you have a hypothesis, you test it, analyze your data, report conclusions, and then it just goes back. You get the data, you question it, and then you have to research again. So for those that have gone through grad school, that's a lot of these processes, not only just to get the quantum computers to work, but as we see these software applications start to come through. So this is the MVP for chemical Q device. So you see at the top, it starts with developers. If you've ever seen that Microsoft video with Steve Ballmer's developers. And with that, it's basically creating something that would have results that are good on paper, but they're not as explainable as something, say 5-10 years down the road with explainable AI. But that's a whiles away. So the key parameters is looking at the ADNI databases. There's PET ADNI, there's amyloid beta PET, there's tau PET. Besides just MRI, as we saw as the previous one. It's a huge field to look at, and this is to get better classification accuracy. And, basically making modifications to QVCs, and also quantum simulators get better. I have a chart towards the end. Basically, it shows, if you increase the RAM, even conventional RAM a little bit, that could open up a couple more qubits for simulator. And depending how the ion trap, neutral atom, and gate-based superconducting continue to progress, that might be a viable option to do things as well as quantum annealing. So primary objectives is to determine the best convolutional neural network to use, optimize epochs, batch size. And this is mostly for the quantum variational circuit, keeping that, because that's working. Like these three other papers are working, and not at this stage to reinvent the wheel. Now, number two is basically start to look at the ion trap as a quantum convolutional neural network analogous to ResNet or AlexNet. Larger feature vector size, these are the quantum benefits, bigger models and data sets. To improve data handling capacity, also to replace eventually this simulated QVC. The goal is not to use quantum simulators. They tend to be really slow. The huge upside is no noise, but just the practicality of it and doing more complex tasks like advanced, what we see with CPUs these days. Now, this is the really unique one. Number three is a principle called explainable AI. So you could see in the previous two, developers were at the top. Now in this specific one, neuroradiologists are at the top. And the whole point is to get this feedback, and you you need to have this interplay between neuroradiologists and developers. So explainable AI is still in its growth, it's still progressing. It's not in a fully established field in conventional computing. So in order for this to happen, that would have to be more common. So something like this, not likely in the upcoming years, but further down the road. And then once ISO sets standards for quantum approval beyond just cybersecurity, for general use, healthcare, finance, those types of things, that would have to happen. And then to have, several quantum clinical trials as well. So I created this quote as an example of a neuroradiologist that would say, I want to understand each major step of deep learning software that is faster, more efficient, and with higher classification accuracy. So the main thing I'm talking about is, number one, the ion trap has this, all-to-all connectivity and it can function, in hybrid mode, in a way that's taking advantage of these big data sets and big models that, quantum promises to offer in medical imaging. Now, this paper in specific, Roche QC, where I've gone through a couple times, this time I went through pretty thoroughly. And in all these things, you need to consider Barron plateaus, cost functions. In ion trap, it's possible to do the fully connected. So as you saw with the previous three papers, fully connected is the big thing. And they had two different approaches to what they do. The first one is similar to what was done in these three papers. The method number two was different. It's just pure quantum. So it's just design and train on a quantum orthogonal neural network. Now, they say as the number of qubits increases, parallel data loading is more beneficial. So, as things start to turn, and especially, as NSF predicts this, practical quantum computer, and then, Time is, putting it on the cover of their magazine, that this is like the new computing technique. Basically, they say it can be used to perform inference on data set in linear number steps. So the reason why quantum is so good for medical imaging is because linear algebra matrices are performed left and right all the time, dot products and these types of things. And it's quantum strength. So sometimes you can inject a little bit of noise, to help. This is talking about overtraining, I believe, and to make the models more robust. But obviously, the main approach is to get rid of it all. But some cases, to use it a little bit. And the models can be quite different. And there's advantages. So you're limited in layers in deep learning by the numbers of qubits, right? So it's just, you have to understand like how quantum mechanics works and how that all plays out in medical imaging. And in specific, they probably had more resources than the average paper, tailor-made quantum simulators, for author-specific circuits. And then, these other things, there's still GPUs that are getting better too. And you have to look at all this. So when you're planning out experiments and, the future of your startup, you really want to understand, what will maintain quantum advantage throughout the years. And this is the paper. They said they ran more than 1 billion shots in total. Now, keep in mind, some are hybrid classical, some quantum, but this is the one, if you were to actually take that and run 1 billion shots on an ion trap, IonQ, quantum computer on AWS Briquette at a penny a shot, that's $10 million. So regardless, because I'm sure they didn't do that, and because, they probably had other arrangements, but it's important to run things initially on quantum simulators is the point with that. Now, Deloitte and Strangeworks, they had this paper last week, and it basically shows some things as far as, you can get, so when it says IQP no fatigue, that's basically on a quantum computer, but the results were not consistent. And is basically reading this, they said the simulator was the best, most consistent, no noise over time. But you could see it's horribly slow, 3 minutes, 45 minutes compared to say 2 seconds. And then the real quantum computer, say like 35 seconds. And they themselves admitted maybe Matik's not the best for error mitigation. And you can see these kind of results here with none in the green. But it's they say it's an art, not a science sometimes. And then this paper I did a review on a long time ago, and then I keep going back to it, but it's basically at its core, explainable AI, is empirical quantum advantage and trying to get it so that you can have some level of certainty if your data is going to have advantage before you even run it. And they, like every other paper, are limited by the hardware. But this I'm really interested in because it lines up with my, that number 3 that I shared before with explainable AI. Now, QEDC is a very helpful organization. So it was formed out of so I think like 2019 Quantum Initiative Act. The funding went to NIST, and then part of the funding went to QEDC. It's based in Washington, D.C. It stands for Quantum Economic Development Consortium. You can pay to be a member. Some things are free if you want to, join webinars, such like that. But this report that they did, it's only 2 pages, and I couldn't include the graphic because it's portrait. It's really portrait. But basically, optimization number 1, machine learning number 2, simulation number 3, the top implemented approaches, in a study of 100 papers, basically. And what's important to know is, yes, quantum annealing is known for doing optimization techniques, but the big thing is that most other quantum computer can do that too, but it's just a matter of time, catching up. Are we talking a year? Are we talking 3 years? As far as, doing these same types of problems. But don't get me wrong, quantum annealing is very established in quantum computing. D-Wave formed, for instance, over 20 years ago. They commercialized in 2011 to Lockheed Martin, bought it for $10 million. So, and it continues. They have over 250 applications that you can use. So it's just limited to certain data sets. Now, the second one, so gate-based quantum computers used in 70% of the cases of the 100, and then the quantum annealers, obviously the 30%. And then, that's the whole thought is if some of these others get better, then, where would that put that, your sole quantum annealing? So some of these, so basically combinatorial problems and many variable capabilities with FDA. And I've gone through ad nauseum as far as, looking at the 521 FDA AI ML approvals and determining, say, a couple dozen, that are the most, relevant in image reconstruction, image segmentation that you keep seeing over and over again. So I covered that a little bit. And this is basically saying, like, if quantum gets this stuff figured out, which is what the funding is indicating, national, agencies, NSF is indicating, quantum manufacturing facility, first half next year, is when you're talking about 50 to 51 qubits, for instance, that's doubling information where in a classical realm you don't. So it'll take a while. So say, for instance, for FDA approvals, you'll likely have to get IEC and ISO, standards created, and then those would be required by FDA a little bit later. And here's, some of the principles. Basically, these are, out of the 521 FDA had, I narrowed it down to 191. And then of the 191, you'll see left and right, reconstruction algorithms, segmentation, those types of things. So here's some of the upcoming stages here. And then, so stage 1 is this Alzheimer's analysis algorithm, which have those 3 funnels, the multicolored funnels, those relate to this. And, there's a number of advantages, with hybrid hardware. and basically availability to bigger problem sets and accessibility to problems never previously within reach. But everything's just very specific. And I didn't include it this week, but I'm working on a slide. And I would say getting quantum advantage, is more mild these days, and it's more specific. But as the more qubits with less error, it's more general. So you can get quantum advantage relatively easier, with some of these things fixed. And especially you'll see for non-deterministic polynomial time, like understanding the specific types of problems that they do better at. And there's multiple different types. So you can diagnose in Alzheimer's, such as the classification, the binary classifications. You can predict, so you have this in data, and then, you forecast what's going to happen prognostically to a patient. And then, validation. So validation is a little bit different because, say, if the blood work and CSF tests are mainstream, and there may be a large number of people getting those tests, the ones they still need confirmation that, they for sure have this. And brain imaging is the only thing that'll show you in specific, even if it's not, showing it as quick as blood work and CSF, what exactly is going on in the brain. They can rule out other things too, tumors, hemorrhages, and the like. And it's a huge field. So they continue to have workshops, these PET workshops. ADNI 4, so I mentioned ADNI in the previous one. So there's 4 total. And like I said, there's actually been shifts. Maybe the MRI is the most established. And maybe if you wanted to do an early paper, probably the best to do. But the PET it's gone through PET, amyloid PET, to now it's tau PET. And there's a clinical trials, basically, requiring either PET and or MRI scans. And this is a paper, this Sabaya et al. And, basically it's looking at, so right now it would be a conventional neural network. And say, for instance, as things move forward, an ion trap, quantum convolutional neural network further down the road. And then stage 2 is basically, the reason why I created stage 2 is because most FDA approvals are based on medical image processing, and that's reconstruction segmentation. So, this is here, and I say as far as the early work, because in order to get reconstruction algorithms, new quantum techniques, start to implement into other things, and you can experiment and test with it. And there's other, Fermi labs working on quantum sensing and quantum computing. And then you have, there's a QSI overseas in Japan. Is it Bosch? It's quantum sensing, basically, too. And there's just an enormous amount of quantum potential, because in all of these things, that's driven by machine learning. Most of the tasks, data acquisition, reconstruction, enhancement, and so forth. You see segmentation. So, looking at all these FDA approvals and looking at, this was a lot of this came from an MIT symposium, and then I think like a year later, it's neuroimaging and machine learning, very specific, and image processing kind of stuff. But basically, insert quantum where it makes sense. And then you'll see. So this is basically clinical trials requires this. So you see MRI and PET. So for a stage 2, you have these huge organizations working on, creating better MRI analysis with better quantum sensors, then, better, quantum computing as well. So there's probably going to be a shift, and we want better brain images using quantum and somewhere along the road. But that's why stage 2 a little bit further down. Stage 3 is basically putting these previous stages together for better benefit, like a reconstruction algorithm and then Alzheimer's analysis. But definitely focused on stage 1 at this point. And then there's a number of precedents in this. You have portable MRIs. You have these, GE has deep learning, algorithms that have been approved. And then these, so basically in everything, it'll present new opportunities, for Alzheimer's analysis initially, as with these 3 papers that are using quantum variational circuits. And this is kind of like the combining, and this is the mission statement for Chemical Q device. So key things for Chemical Q is licensing, subscriptions, partnerships. I've had some bites with these, kind of have like some top, organizations in the world following me at this point, which is good. And then the ask is basically for experts, medical experts, quantum experts. Be nice, to get programming on this. KISS kit, penny lane, especially with stage 1. And R&D efforts should begin ASAP. There's no reason not to. There's 5 different types of hardware modalities on AWS Briquette. And, we see the papers, with good results, mostly simulators. But it's just basically fill in the blank as the quantum computers get a lot better. And, there's advantages basically in quantum for complex samples, right? So if you start to figure out things at 50 qubits, 100 qubits, now you're talking 1,000 qubits in imaging. And that's not even considering the whole, everything that's going to be later on with simulation, that it makes sense to use quantum for brain imaging. It's a complex sample, more complex than blood and CSF, cerebrospinal fluid. So here's some of the progress that's been made. So the industry is primed, I would say, at this point, and then it's just, insert better quantum computer, get more resources, get more capabilities to start putting things into action. This is an available pitch deck, so more conventional, say, for investors. And then there's a bunch in, say, AI quotes. The one I'll go to is the 2023. Artificial intelligence can reconstruct coarsely sampled rapid MRI scans into high-quality images with similar diagnostic values as those generated through traditional MRI. So, it's basically saying, like, I've other companies do similar types of things where you just have a single coarse-grained MRI, and then you apply an algorithm. And then, you don't have to do as many scans because it can tell, basically it cuts time in pieces, less, it takes less time. And there's a number of, this is a really good slide because it's the background for quantum convolutional neural networks, talks about barren plateaus, efficiency, instantaneous quantum polynomial encoding, and then basically QNNs can be trained similarly to neural networks. And again, there's applications that quantum might not be needed for, but the whole thing with matrices, linear algebra, quantum mechanics is lining up well with medical imaging or imaging. And here's basically a reference slide, quantum artificial intelligence, QML, quantum neural networks, and the biggest one. So quantum convolutional neural networks has the most, has upside because it's less susceptible to noise. There's always, especially in coming years, likely going to be some aspect of noise that you might not want. And the number of publications that you'll see in quantum is not quite reflective of what quantum can do. It's just that they're running well, on today's simulators or noisy quantum computers. And then basically, from what I've read, so you'll see a quantum variational circuit, like 4 qubits, and this is 10, right? So then you keep bumping up, and that's what they say is this, you can start to run ion trap quantum computing experiments because of its all-to-all connectivity. So it's a huge thing that, it's not just nearest neighbor in this case. So, keep your eyes posted, especially with the headlines coming out. Gate-based superconducting qubits, likewise, they came across this thing called dynamic circuits. And I think other technologies, hardware technologies can use it too. So it chops up quantum circuits into pieces. And then, these days, the quantum simulators are getting the best results. but they're limited in qubits because of the RAM, resources it would take to run. I saw one paper, I think it was 49 qubits, but it's probably not close to functional. I haven't seen as far as like the applicable, like an application, anything above say 30 for quantum simulators, but they're typically slow. And there's all these other techniques that's being experimented with, including explainable AI. So definitely check out the time cover, the quantum leap. It's a huge thing, right? So it takes a lot of belief in a technology to put a quantum computer on the cover. And I don't think they felt confident a year ago. So it's a good sign. NSF still says practical quantum computer this year. And then MIT is basically shifting everything, from this concern of the quantum computers to more consolidating your years of research. Now, a number of driving forces: IBM, Cleveland Clinic, NYU Langone, Fermilab. The progressive hospitals are Cleveland Clinic, NYU Langone, Mount Sinai Hospital. Two of them are in New York based. But, people see that potential, and you just have to understand, like, yes, now's not the exact time to get awesome performance, but it totally makes sense to start, running on Amazon Briquette, their rental service. And then there's a number of these good research papers in QML. QML is not a new thing in healthcare. It's just the results have not been awesome the past year and a half to 2 years, but we're starting to see better. And then this is a new slide. So perspective in quantum. So ion trap, better qubit coherence, flexible connectivity. That's a huge thing. Gate-based superconducting qubits. Not running circuits on a huge circuit on a quantum computer. Neutral atom, better relative coherence, if not some of the best. But I haven't seen it too much in papers. So I would say that's kind of like the dark horse out of those three. It does take a fair amount of, all different types of data, where the other two have experience where I don't think neutral atom has, but no cooling required. Photonics, gate-based, it's a very desired platform. They said, if you can get it to work with photonics, but I think that's a little bit further out. It's room temperature, you have flexibility. Silicon spin is kind of like this, like we could have 1 billion qubits was a phys.org in relation to a Nature paper. Most of these are, in big journals, these links. But, it might be some time too, but you just have to be aware of what's going on. Quantum annealing is the most established out of all of them, but it's only for optimization problems. It's a proven method, right? So if you want to get your foot in the door, it's just with annealing, some of these could, get better significantly within the next year or two, and they can also do optimization problems as opposed to just quantum annealing. That's mostly what they focus on. Now, the one that most people don't know about is quantum RAM. So there's been this Harvard, Caltech, Google, lots of Harvard. There was a Google, basically a web blog on this. And Harvard achieved over 2 seconds in quantum memory. And then they also work on a lot with, computing. That specific application was for networking. But the Google, Caltech, Harvard paper, using less than 2 seconds, they used the Google, this is the quantum supremacy of 2019 in October. And they were able to mitigate error so that it wasn't so much the principal component of what they were trying to do. Now, the last one is like, yes, if we have a RAM breakthrough conventionally, I don't think it's going to be, because it's just, and so I think it's something like an exabyte of data for something like 26 qubits to simulate on classical. It's just an enormous amount of resources. So you can experience minor gains as RAM gets better, classical RAM, conventional RAM, and it also remains noise free. But the really cool stuff, with qubits, if you look at charts, and especially, consistent quantum advantage, figure hundreds, thousands, 10,000s of qubits. So it doesn't look like that's as feasible, that last one. Here's some more specifics about I would say the two kind of leading ion trapped superconducting qubit. And again, neutral atoms in the race. They just got DARPA funding. Photonics is in the race too. They just got DARPA funding too. So, the show's, is still going on, but I would say that, some of them kind of have clear advantages, those two technologies. And this is kind of like with testing. So blood plasma versus cerebral spinal fluid with neuroimaging. And I kind of touched on that a little bit before, but basically, there's other things, neuroimaging will remain to be used for, even as the other two are breakthrough devices and come into their own less expensive testing. So Alzheimer's Association says $1 trillion, worth it'll cost the U.S. by 2050. Last year, they said over $300 billion. A lot of these are caretaker hours. Now, what I'm talking about with these papers and classification is basically, it's a more detailed test. It's actually physical, tangible. If somebody once showed me just recently on an electronic device, just like blocks with numbers in it, and it didn't mean anything to me. But then they showed me an image, of what was actually going on site, and I was like, oh. But then you can combine that image with that data, and then say, you're more on that same page. So, anyways, imaging should remain strong. And, mechanistic details, ADNI, loni. So loni is the Laboratory of Neuroimaging databases. They host the ADNI, and it's a continuous thing to further understand the brain. And like I said, anytime you're talking complexity and imaging and matrices and linear algebra, you'll likely see quantum computing applications show up in other places too. So this is the president of the United States. Our president went to upstate New York and looked at a quantum computer with IBM CEO, and then the New York Governor Kathy Hochul as well. And the quantum is a government initiative. This is nothing new to White House administration. They're bringing on people. They brought a bunch in December, new quantum cybersecurity law, those types of things. So that's I think some people think that it's basically this the industry's driving everything, but I would say the industry is better at say innovation. It's more open, but the government's been working on ion trap. They call gate-based superconducting, they call that transmon qubits. And, quantum networking, it's just, they can only take it so far, then it gets opened up, or it more like gets adopted by industry. And then we really start to see the fruit of all of this. So I'd be interested, kind of like on that Alzheimer's take, should be able to come on, and then chat should be good. So yeah, any questions, regarding any of the papers, any of the 3 Alzheimer's quantum variational circuit papers?
Hey, Kevin.
Yeah, go ahead.
So some of those papers were showing quantum processing of like MRI images or some sort of medical image. And I understand you got these algorithms and this information from one of the various papers that you've just distributed and stuff. Do they actually include some images of the like before and after type of thing to show what is the quantum piece of it doing and what is the classical piece of it doing?
Could you be a little bit more specific as far as image?
Well, it's like one of the slides you had, it was it appeared to be like an MRI as an input, but there were only like four qubits in the circuit. I think you mentioned that the four qubits were basically an encoded four-dimensional vector, which is cool. But I guess that means they must be sliding that operation via convolution window over the MRI image.
Yeah,
And in the case of MRI, it would be like a voxel window or
yeah.
a three-dimensional window. So did they give you any indication of like if this is the input voxel, this is what we get out of it, sort of thing?
Yeah, I know in specific for convolution, I think that's just like the ResNet and AlexNet. I don't think there's any type of convolution pooling in the quantum variational circuit. And as far as I know, with like say if you have 30 epochs and then you're sliding and then you go back and then you're sliding and then you're improving your results every time. With these, I I've read in other papers where that they said that we wish that we could have used the raw data. Now, by raw data, I think that means voxels. Now, I downloaded the Kaggle, and I know for sure that that's just 2D. They're just flat images. And then, unless somebody else knows, I would say that ADNI. I think some of these are just 2D, right?
So that they were doing like a single two-dimensional slice through an
I,
MRI,
I
maybe.
I think so because, like I
Okay.
said, the data requirements to to do raw images, and even if they're only like 512 by 512, and then don't even start talking about PET that's 3D because of RGB. Um, yeah, I think that these studies would use 2D. I didn't see any mention of any like 3D voxelized. And again, the closest where I've got to it, where other papers say they were a little bit disappointed with their results, and they would want to switch to raw data. Um, and I think that's where you get into the huge file sizes.
Yeah. You also mentioned that you had downloaded a data set
Yeah, you
of
can
images.
download if you look at the paper, you might be able to just find it. It's a Google Kaggle. And there's a specific author that put all these together. They've got 4 folders. So you can go through each of them. So there's sometimes they're not like mainstream, like it's like uh, very mild or moderate. And I had to look up as far as where that lines up as far as progression of Alzheimer's. But I know in at least the Kaggles is they'll just choose 2 of the folders, say the least and the most, least demented and the most demented. Yeah.
So these are data sets that have some sort of medical imaging related to Alzheimer's
Yeah.
included.
Yeah. So, there's correlations between brain atrophy and Alzheimer's. Hippocampal atrophy in specific is usually the first to go. So it's interesting, but that specific one was 6,400. But I don't think all of it gets used because in one of them they were saying 100. Let's see, 100 demented and 100 non-demented, and then a confusion matrix. Basically to show their results. So if it's 98%, then only like say 2 were off diagonal.
Yeah. Did you happen to know what the size of that data set was that you downloaded?
Um, it's not that large. I have it.
Okay.
I see the zip right now, but let me see what the zip is. I want to say 35 meg. Yeah, 34 megs for the
Okay.
zip. Or yeah,
Um,
un, the smaller one is 34 megs.
okay. Did you attempt to recreate the paper's work by doing some of the processing on that, or
No.
okay? Um, the reason I'm asking that because I have had this. This is going to come on and work. I have had this Jetson Nano, for some time, and I've just been too busy to get it into a case and get a proper power supply. But even if you run this thing balls out, it only draws about 5 amps at 5 volts. That's 25 watts. This this thing on the top, if you can see it, the heat sink is basically on the module. The module is plugged into this carrier board, which has all of the peripherals on it. But this is Jetson Nano. This has almost half a tera-op of performance. So that's like almost 500 giga. It's like 460 giga-ops. So that's 460 billion operations a second. It's just this one little guy can do.
Yeah.
So I want to put
That's
this
like
to
a souped up Pi then, right?
well, it's a little bigger than a Raspberry Pi, but souped up is putting it mildly. I mean, again, 460 billion operations a second, just this one little bit, and this is the smallest one they make. They've got some bigger modules that are, now this was a developer's kit, so it was fairly inexpensive, and they supposedly have some new developers kits, but some of the bigger Jetsons are in the 20 to 40 trillion operations per second. So I'd like to find a machine learning project for this guy and just see how hot I can get it.
Yeah.
I finally got around to building a power supply for it.
So that's 20 teraflop?
It's there. You got to be careful to call them flops. They call them operations. But the ratio of operations to a floating point operations can be it's 1-to-1, somewhere between 1-to-1 to 2-to-1, depending on which floating point operations you use. So yeah, this guy it's 460 giga ops, so that giga is a billion, right? So 460 billion operations a second. And the bigger ones, the next bigger one is in the or they have a couple of bigger ones. The one's called the Xavier. You're looking at 20 to 40 or to 60 tera operations. So that's 20 or 40 trillion operations a second.
Yeah.
So lots of performance.
So while we have a sec here, so Ron is talking on Saturday. I'm going to try to catch it. I got a hiking group, but it's 10 my time. I think it's 1 Pacific. You can put the link in the chat. And Ron's come on this one before. Ron has a, I would say history of computing that some of us look up to. Anybody else? Any other questions or comments? See a number of familiar faces here. Hannah or Bahar?
Hi. So this is Hannah. I really enjoyed the talk. I had actually reviewed a previous paper regarding QML, but instead of for image classification, which I know it's which is what Chemical Q Device is kind of focusing on. I was also looking at how they're using frequency detection. So in things like EEG, magnetic waves, and analyzing that through the MRI channel itself rather than image data. And I was wondering if Chemical Q Device, as the company, would want to kind of incorporate that at all into any of its kind of classifications of Alzheimer's, or is it just strictly image classification at the current kind of standard?
So image classification is relatively easy because it's pre-existing images, and then you're just doing things to it. Medical imaging and just imaging in general, you'll see many papers that refer to images to test things. just because it's an effective way of doing things. So, I mean, what you'd mentioned, the EEG frequency, it reminds me of diamond quantum sensing for that first layer of, medical image processing, like detection. And there's been a number of good reports. I might be talking about some that you had mentioned, but there's, Nature, QPSD, there's Nature, they did millimeter resolution on a rat's heart instead of centimeter resolution. And then quantum sensing is not new, like quantum computing. Quantum sensing just has to rely on some aspect of quantum mechanics. So that's like my stage 2, where you have detection. Now, on the software side, that's more like reconstruction algorithms or like segmentation in
Right.
stage 2.
Okay. Yeah, because I think that the paper that I read, which was specifically looking at QBoost, which is something that they're kind of incorporating into the layering of the machine learning algorithm, that basically, in the name, it just boosts up performance, and specifically looking at kind of optimization of the peaks and valleys of the frequency. So, how can you tunnel to get essentially using quantum to get quantum tunneling to basically get the lowest, to correctly identify the lowest point of that frequency, sort of in those peaks and troughs. So that was kind of interesting. I think it was Duke University that's kind of the one that I was kind of going over and analyzing. But yeah, but it was great that you mentioned some others that I'll probably take a look at as well.
Yeah, and there's papers out there as far as quantum data, classical data. I think it's the big table of artificial intelligence, the big quantum table of artificial intelligence, something like that. And the first table says quantum machine learning, and this goes back to 95. But there's 4 different types. There's, depending on classical, algorithms and data. So you have a CC, which is classical of both, CQ, QC, or QQ. And I think most of these that are being done today are QC or QQ. Now, as it relates to the quantum sensing, so these papers, especially the first 3 in that chart there, they're more, it's classical data, and then there's 512 features to 4, and you're doing this, a quantum variational circuit back and forth, and then it gets decoded back into classical. There's a paper out there, it's Los Alamos National Laboratory, and it says the challenges and opportunities of quantum machine learning. Quantum machine learning, includes quantum neural nets, quantum convolutional nets, all that kind of stuff. But they said definitely, supervised learning, and the more quantum you can get with your data. So if you have quantum detection, it's all quantum. The more likely you'll have quantum advantage. That might take so today we have exponential classical data. So it's going to take a while to get to that point where we have exponential quantum data. But there's stuff, what I see in 3 years that's in line that people aren't even talking about too much these days, because we're mostly aiming at hybridness now, like, classical data to quantum.
Right. Yeah, I know people often assume that quantum is going to, they hear the word quantum and it's like, oh, it's going to, replace classical, but they kind of work in tandem, I think, and that's kind of, important for especially in the medical field as well. And I think you mentioned also, getting the neuroscience community kind of a bit more educated in the quantum landscape. I think that they're slowly kind of getting to terms with it, but I think, obviously as we kind of progress through, these stages and getting more and more, research, and I think, getting that education to the medical team as well to prepare for stage 3 and then FDA and all of that. I think that's going to be pretty crucial as well.
And I think a lot of them, and I know if you're a neuroradiologist, you have to take like 5 years after med school or something crazy like that. and then it's another year, or it's radiology is like 5 years after med. It's an enormous amount of time. So they've probably taken classes in quantum mechanics. The one that rings a bell, medical, maybe like a medical technologist or something like that. But they really understand the physics behind all of the operations and all these
Right.
specific
Mm-hmm.
medical devices.
Mm-hmm.
So the new thing is the computing. So quantum
Right.
computing hasn't worked sufficiently enough for especially medical, but
Mm-hmm.
finance or transportation that
Mm-hmm.
is still kind of working through. I would think that's probably the biggest hurdle, and it's the complexities of, is say people come out, one person comes out with, three people come out with one thing, and then, which standard should we choose? And, especially with hardware, I think there's lots of people in IBM Qiskit that think that it's going to be, that's the thing to use. But I would say for imaging in specific, especially for all-to-all, fully connected layers, for ion trap at this point. But yeah, I'm sure it's just a time thing, because there's an AWS article that says there's decreasing number of neuroradiologists or radiologists, I think it was in general, and the platform is going all towards theirs, AWS, Microsoft. They late last year they announced these imaging platforms that probably does a mix of neuroimaging, neuroradiology, those types of things. But I've touched on some of those papers, and they go over as far as like the current status of not all radiologists know or care about AI. And if you're in a small town, it might not be for another 10 or 15 years, that you really have to. And everything's getting more automated with services too. But yeah, some of those that you mentioned, so the QBoost I've heard of, I haven't researched too much. Quantum tunneling, I missed. It was a quantum biology meeting today. They talk about that almost every meeting. But yeah,
Right.
Duke is definitely in the mix. Pentagon, they're close to all that,
Mm-hmm.
and I think they've done some of that. So it's just interesting,
Yeah.
seeing
Yeah.
quantum in all these different organizations,
Mm-hmm. Mm-hmm.
partnerships.
Right.
Anybody else we haven't heard from? George, Bahar, or I think John.
Just thank you, Kevin. As always, it was very informative. Awesome. Thank you.
Yeah, you're welcome. And then George or John? Oh yeah. So this paper here, I've come across before. Thanks for sharing.
Mm-hmm.
But it talks about QCNNs, I think. But in my experience, the QCNN seemed to be a little bit further off. I think this is more, what's this, like 2019? It is more like setting things up, I think, at this stage. 2020. So yeah, thanks for sharing. Anything else? And you can come on again.
I wanted to make a comment. You had mentioned the big DARPA grant that they just issued. It was interesting to see that they are backing a few of the dark horses, so to speak. They're going after the technology that hasn't quite got there yet, like braiding and neutral atoms, and I think there were two other ones. I can't remember what they are, but I think that's pretty cool that they're like they've made a decision to go and try to push these alternate technologies to see if it's enough to get them into the practical zone.
Yeah. Some of their forecasts out were a little far. I think like 5 or 10 years. But I think the biggest ise is the number of publications in reputable journals. And I would say Ion Trap had the most in, say, like Nature. Because I have a subscription. And then, there's just a volume, definitely the gate-based superconducting qubits, and simulators too. But you need to research a lot, before you can start implementing into the next step. Like lots of different data, lots of different types of projects, not just image classification, but finance and transportation and all those things. And D-Wave, they have a lot of corporate partners. So there's for specific tasks, but if you look at their website, there's over like 250 quantum applications that they've done to optimize things. And the government's bought into it. Lockheed Martin, 2011, $10 million. So I think there's one at USC, a little far north of me here. They have quantum annealer, but yeah, the new stuff, and especially for medical, because people touch on physics, and I think quantum mechanics. I've taken certain courses that had aspects of quantum mechanics, but that's the thing. That's the differentiator, is computing numbers and doing things with them, as opposed to just quantum sensing. And you have quantum communications, cybersecurity, but those use quantum computers too. So anybody else we haven't heard from? Any other last questions, comments? Ron posted in the chat, quantum physics nonprofit group. I'm assuming that's the Chicago one that I go to every week.
Yeah, it used to be Quantum Computing with Anna. She incorporated a not-for-profit and changed the names on everything.
Isn't it like Quantum Physics Corporation?
I don't want to get involved. She's actually incorporated here in Illinois, Quantum Physics Corp.
Yeah. So Anna has a breadth of knowledge, I would say, medical. Doesn't she she's an MD, and then
she's a she's studied lots of physics and math. So yeah, she's a good resource. And the talks we have over there are really getting into the nuts and bolts of quantum, and be prepared not to understand all of it right away. Because I don't think anybody does, but there's a lot of good topics over there.
Yeah. And I think she does collabs with Washington, D.C. And
yes,
unless you're hiding under a rock, Ron is all over with his meetup on Saturday there. That events in the chat there too.
Yeah, it's a Saturday. It's 12 noon Chicago time, 1 p.m. Eastern time. So I guess that's 10 a.m. West Coast time.
Yeah.
It's basically the same talk I gave here in Kevin's group. I've added some stuff. A lot has happened in the last 6 months. So hopefully a lot of people will get a lot of good out of it. So I'm on over.
Awesome. Yeah, like I said, I'll try to chime in. I have a hike at 8:30 with a bunch of people, and then I'll have my alarm set to 10. What would that be? 9:59 is what I usually do.
Okay.
Oh, thanks for sharing that. I think that was Hannah, right?
Yes. I'm actually going to be attending that, so hopefully, I know there's a bunch of I think they're focusing on tomographic image reconstruction, so may or may not. It includes hybrid solving as well. So, so I think that's in 2 weeks. Yeah, February 28th, at 12. I think it's 12 Pacific time, because I think D-Wave's on Pacific time.
Yeah, I'll probably register to that. I appreciate that. But yeah, reconstruction is a huge area. There's MIT is in this space. So Seth Lloyd posted or published all this stuff without a working quantum computer. It's really quite amazing. He's MIT.
Yep.
But yeah, image reconstruction is probably the top, if not the top, FDA approval for like radiology and neuroradiology. So you'll see a lot of deep learning. That's interesting. I wonder if they mentioned that, if it's deep learning. But the trend in 2022 is deep learning a lot, like deep learning reconstruction, deep learning segmentation. But yeah, I'll definitely look into that. I appreciate that. Any other last questions? We still haven't heard from George or John there. George says thank you. And then if not, this is episode 69, February 9th, 2023. Thanks everybody for coming on to listen about healthcare and quantum technology.